Welcome back to Pre-Calculus. We're going to continue our discussion today looking at limits towards infinity. So there's really a lot to limit towards infinity that you're going to learn a little bit more about even in calculus, but we're just going to kind of intro it a little bit here because for the most part, it's pretty simple. So one more place limits are used to is to explain the end behavior of a function. So, we're learning this lesson on limits because there's just so much that limits help us do. They really do open up these wide open doors to all kinds of more mathematics. So in the past, we described the end behavior of a function like this. If you remember on our lesson over function analysis, we said, hey, as x approaches infinity, f of x approaches what? And we filled that blank in. And then we said, okay, that's the right end. That's going towards the right, towards infinity. But if we want to go towards the left, that's negative infinity. So we also said, all right, as x approaches negative infinity, f of x, excuse me if I'm messing this, approaches what? And then we looked at the function and we kind of said, hey, as we look way to the right, what's the function doing? As we look way to the left, what's the function doing? So that's kind of how we approach end behavior in the past. But now we could talk about end behavior through limits. And actually, if you understand what I wrote down there, it actually makes so much sense. So here we go. Here are limits towards the ends. These are called infinite limits or limits towards infinities. So the first one is saying, hey, what is the limit as x approaches infinity? So this is saying, hey, as we go way to the right, what is our function doing? So again, it's asking you what the y values are doing as x gets really, really, really big in the positive direction. So as we look further and further and further to the right towards infinity, what is the limit of our function? This is literally no different than using that notation. As x goes towards infinity, the function is going towards what? This is exactly the same thing, right? We're just using a limit to define this and to write it nicer. So once again, here's looking towards the left. This is the left end behavior. What is the limit as x goes towards negative infinity? Negative infinity is towards the left. So again, we're asking what the y values are doing as x gets really, really, really big in the negative direction, okay? Notice I'm not saying really, really small, because if x gets really, really small, that actually means closer to 0. No, we're not talking about 0 at all. We're talking about going way to the left, which is a negative big number, negative infinity, or way to the right. So one way we could answer these types of limits is with our calculator. Calculator actually makes it really, really fun and easy to do. So let's go ahead and show this real quick for you. So the first thing I'm going to do, like for this first example, it says, what is the limit as x goes towards infinity of 2x squared minus 5x? So once again, I'm just going to go into y equals here, clear out anything that's there, and I'm going to type in 2x squared minus 5x. All right, and then I'm going to go second quit to get out of there. And I could go vars, y vars, similar to how we did with looking at limits. But this time I want to go right to the right. So, what's a number way to the right? 569. I mean, that's a really, really big number way to the right. And I get 644,000. Then we say, okay, well, let's go further to the right. Let's go really, really, really to the right. So 89,752. So that's a pretty big x value way to the right. And now look how big this number is. Again, I got to move that decimal 10 times to the right, and that number is honestly astronomically large. So it looks like as x gets bigger and bigger and bigger, my function just keeps getting bigger and bigger and bigger. And that makes a lot of sense. The other thing you could do too in your calculator is make a table. This is really cool. So all you got to do is go to second window, which is your table set command. And we could say, hey, let's start the table at 0. And let's count by 100. So that little triangle means delta, which is change. So how do we want our table to change by? So we're going to have it start at 0 and change by 100. And then to hit the table, we're going to hit second graph is the table command. So notice that our x's are going by 100s. So as we get bigger and 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 bigger, notice the y values are also getting bigger and bigger and bigger. And again, watch out for those e's. Like you'll see e to the 6. That means you got to move that decimal to the right 6 times. That's a really big number. So that means that our answer is going towards infinity, right? It's getting really, really, really big, which you could say does not exist because it means, when we talk about a limit, we want to converge onto a value. So technically, infinity is not a value to converge on. So I'd be okay with you saying D and E there as well. But another way that you could think about this without your calculator is just think, all right, if I plug a really big number in for X, and you think, what's going to happen, right? Well, a big number squared is even bigger, times that really big number by 2, and I'm going to get a double big number, and then I am going to subtract 5 times the big number. But again, excuse me, 5 times a big number is a big number, and you're subtracting it, so it's actually going down, but you got to think of it in terms of like a big number squared times 2. When you square something, it gets really big. So subtracting 5 is just really not going to matter that whole much. It's still going to be a really big number. But again, the calculator does a nice job showing you that. Let's do a second example here. So again, y equals, clear that out. Be careful. I'm going to go alpha y equals to make a fraction here. So I'm going to do 2x minus 3 divided by x plus 4. Quit out of there. Vars, y vars. Now this time they want me to go towards negative infinity. So negative infinity would be like negative 1,200. And I get this fraction, okay? Now I don't really like, I'm not saying I don't like fractions, but sometimes it's better if it's a decimal. You can actually read it a little bit better. So basically that's really, really close to 2. And then I get, okay, I say, well, let's go even further. So vars, y vars. Let's even go further. Oh, I typed in, did I do negative? Yeah, I did negative. Sorry. For a second there, I thought I didn't do negative. I thought I was going to the right. We definitely want to look to the left. It says negative infinity. So let's try to go really far, right? So we say, what's an x value way to the left? Negative 2, 5, 6, 8, 7, 4. I mean, that number is way to the left. And then again, we're clearly converging on 2. Clearly converging on 2. I mean, it's just getting closer and closer to 2. If you want to set this up as a table, second table set, start it at 0, and then make the table go, heck, make it go by 500s if you want. And then second graph. Now, we got to go up to go into the negative. So notice if I go up, my x values are getting more and more negative. And now, the y values, I'm so sorry, I'm coughing. The y values are getting closer. Now, they give you fractions there, which I hate. But, the reason why it's doing that is because I typed it in as a fraction when I go to y equals. So if I would have typed that in without that little alpha command, it would have done decimals. But the point is, I'm getting closer and closer to 2. All right, let's try this next one here. Once again, y equals, clear this out. 2 times 3 raised to the x. Quit out of there. Now, this time I want to look to the left. Again, it says negative infinity. So please make sure you're checking those little details like that. So now, again, let's go, negative 875. That's pretty far to the left. And wow, it's just telling me 0. And I say, well, let's go further to the right. So let's just add on some zeros there. Further to the left. Negative 87,500. And again, it's just telling me 0. So again, I do have a limit as I go that way. I'm going towards 0. So now let's talk about what's happening on these problems. So let's explore how we can understand end behavior without actually using our calculator. So let's talk about end behavior. So there's many different types of functions out there, but one type of function is a polynomial function. So a polynomial function, the end behaviors of all polynomial functions are boundless. Boundless means that they don't exist. They either go towards infinity, infinity, or negative infinity. So you really don't have any bounds. That's why it's called boundless. So we're going towards negative infinity or infinity, which again means does not exist. Okay. Now remember, if you're talking about polynomial functions, if you have an even degree, that means both ends are going up or both ends are going down. So x squared, x to the 4th, x to the 6th, x to the 8th. Both ends are going up or both ends are going down. How do you know if they're going up or going down? Well, that depends on the leading coefficient. The leading coefficient is positive, they're both going up. Leading coefficient negative, they're both going down. Odd functions, one end is going up, one end is going down, but they're still boundless. The limit still does not exist because we're not approaching a number, we're just going up and down forever. Now again, how do you know which one's up, which one's down? If your an odd degree, x cubed, x to the fifth, x to the seventh, so forth, or even just x, it's leading coefficient. So if your leading coefficient is positive, the right side is up, the left side is down. If your leading coefficient is negative, left side up, right side down. I actually have some pictures here to show you of this. So these top two are for even powers, x squared, x to the fourth, you get the point. Leading coefficient's positive, both ends are going towards infinity. So again, the limit overall really does not exist. Or if the leading coefficient is negative, both ends are going down towards negative infinity. Once again, the limit really does not exist because, again, you're not converging onto a specific value. Odd powers here, positive leading coefficient, right side up, left side down. Negative leading coefficient, left side up, right side down. But again, you're boundless. You're going towards infinity or negative infinity, which really means the limit does not exist. All right, let's talk about rational functions. Remember, rational functions are defined as a function that has a numerator with an x in it and a denominator with an x in it, right? So remember here, the end behavior can converge onto a value if there's a horizontal asymptote. We've actually talked about horizontal asymptotes a while ago, but if there's a horizontal asymptote, as you go way to the right or way to the left, your limit really does go to, you are bounded to that horizontal asymptote. So let's briefly remind you how to find a horizontal asymptote. So you have to compare the degrees of the numerator and the denominator. If the numerator degree is smaller than the denominator, you automatically have a horizontal asymptote at 0, which means the right end and the left end, as you go towards positive and negative infinity, are both 0. If the degrees are the same, then you divide the leading coefficients to get the horizontal asymptote. So if your degrees are tied, then you divide, let's say you divide your leading coefficients and you get 5. Well, that means your limit as you go way towards infinity is 5, and as you go way towards negative infinity is also 5. If the numerator degree is bigger than the denominator, you have no horizontal asymptote, so you don't have to worry about it. Once again, it'd be considered boundless. The limit towards infinity or negative infinity would not exist because you're boundless. You're just going up or down forever and ever. So let's look at a graph. So here's a function, kind of a weird, but definitely a rational function here. And here's a graph of that rational function. Now, the first thing is, we love graphs, right? Graphs always make limits easy. But we clearly see there's a horizontal asymptote at 2 here. But just to confirm that, look, your degrees are tied. Top degree is 2, bottom degree is 2. And when that happens, you divide your leading coefficients. 8 divided by 4 is 2. So we have a horizontal asymptote at y equals 2, which we could clearly see in the graph. So the limit of this function as x goes towards infinity is going to be 2, because as this purple graph goes further and further and further to the right, the y value is approaching 2. So we are converging onto a y value of 2. Never going to get there, but we're getting really, really close. And the same thing can be said even if I attach a negative infinity, because as we look to the left, it's doing the exact same thing. It's converging onto 2. So make sure you understand that that happens when you have horizontal asymptotes, okay? So if your degrees are tied, divide to find the horizontal asymptote. If the top is smaller, automatically 0. So that makes the answering then pretty easy, even if you don't have a graph. All right, now let's talk about exponential functions, where we have a times b raised to the x, which means the exponent is in the variable. I keep messing that up. The variable is in the exponent. So in these exponential problems, one side will converge onto a value, okay? Growth functions, the left side goes towards, okay, so if you're a growth function, the left end behavior towards negative infinity will approach 0. If you're a decay function, the right end behavior towards infinity will also approach 0. So let me look at some graphs of that real quick here. So this first one is a growth function. We see that as we go from left to right, the function is growing. So this means that the right end behavior as x goes towards infinity is boundless. It's going up forever towards infinity. But the left side is going towards 0. So the limit of this function, that's a growth function, as x approaches negative infinity would be 0, because that left side's approaching 0. If we flip it around, this is a decay function. So as we look from left to right, the function's decaying. So that means the left side is boundless, going towards infinity. The left side's going up and up forever. The right side, as the limit of x going towards infinity, that would be bounded towards 0. That would be converging onto 0. Now, please make note that you can transform these graphs. You could transform these graphs by moving them up or moving them down, and that could affect that value, right? So for example, if I take either one of these graphs and move it down 5, now all of a sudden that horizontal asymptote is going to be at -5, so the limit would be -5 to the left or to the right. So make sure you kind of understand that as well. And that's an advantage of having the graphs. I mean, the graphs make finding limits really, really, really simple. All right, let's talk about logarithmic functions. Logarithmic functions, both ends are boundless, although it may not look like it. So here's an example of a logarithmic function. And some people say, oh no, the left and the right side, they're going somewhere. No, they're not. Listen, first off, if I said, hey, what's the limit of this function as x goes towards -infinity? Well, that would be a DNE, because the graph isn't even allowed to go toward -infinity. It's basically stuck with a vertical asymptote at 0. So as I go further and further and further to the left, there's nothing over here. I mean, it's just empty. So, excuse me. The better question would be, what's happening as we approach 0? Now, that's not an infinite discontinuity. Boy, I just keep falling over my words in this video. I'm sorry, guys. It would be an infinite discontinuity. As I approach 0, the function is going towards -infinity. Again, as I approach 0, the function is going down, down, down. But that's not an infinite limit, right? Infinite limits look way to the left or way to the right. As I look way to the left, there's nothing there. It's not even allowed to go over there. And the other thing is this. A lot of kids will look at a log function and they think they see a horizontal asymptote here. No, absolutely not. They're just really, really slow. This graph does go up boundless. It will eventually approach infinity. It's just doing so very slowly. If you think about quadratics get big really, really fast. But logarithmic functions, they get big just really, really slowly. So these will not have any limits, left or right, because both sides, well, the left side's going nowhere, so that does not exist, but the right side is going towards infinity. All right. Now let's talk about trigonomic functions. These have limits where the end behavior does not exist. If we're talking about our good old friend sine, remember sine is this function that's just doing this. It's bouncing back and forth between 1 and -1. It's never stopping. And even our friend cosine is doing the exact same thing. It's never stopping in both directions, mind you. Sorry that this is looking terrible, but you get the idea, right? So it's not converging onto any value. So the limit when you're involving sine or cosine is going to be does not exist, because I'm talking about just sine, right? Just sine of x, just cosine of x. Those limits towards infinity or -infinity don't exist because, again, as I go further and further to the right, which is towards infinity, the values are just bouncing back and forth. They're not converging onto a single value. And remember, for a limit to exist, even these new infinite limits, you need to be converging onto a single value. Now, lastly, this is pretty cool. We could tie into what we learned last unit on sequences, is that we can actually talk about the end behavior of a sequence, because remember, an arithmetic sequence is nothing more than a linear equation. So like 3n plus 2, that is arithmetic. It's also linear. So if we're talking about the end behavior, this is basically a polynomial, right? This is a straight line. And the end behavior is boundless. It does not exist. Because as I go further and further to the right, the function's going towards infinity. As I look further and further to the left, the function's going towards -infinity. So, listen, if I say, hey, what's the limit as x goes towards infinity of this function, which is a sequence, which is linear, essentially it's a polynomial. I mean, you could put an answer of infinity. I'm not going to mark that wrong, but technically the answer is does not exist. Because for a limit to exist, we need to be converging onto a value. So anytime you put infinity or -infinity, you are, as your answer to a limit, you are essentially saying that there is no limit. You're saying that's boundless. That means it's not converging onto a value, which means there is no limits. You're essentially saying DNE. But watch out, because remember, we also learned about exponential functions. And an exponential function is geometric. So that looks something like this, 3 times 2 to the n minus 1. That is a geometric sequence. And remember, geometric means exponential. So now we're just back to the exponential that we already talked about. If your b value is greater than 1, you're going to be a growth. So that means the right side, The right side is boundless, it's going towards infinity, but the left side is bounded towards 0. So the limit as x approaches negative infinity would be a specific number, 0. If your b value is between 0 and 1, that means you're a decay function, and this time the right side is bounded towards 0 as x goes towards infinity. The left side is boundless, it's going up forever as x goes towards negative infinity. So when I talk about sequences, all right, if all I'm doing is replacing x with n, it just doesn't matter. Remember, arithmetic is still linear, which is polynomial. And geometric is exponential, which is exponential. So we know how these functions behave. So at the end of the day, you need to be able to answer limits based towards infinity or negative infinity. One way that will always work is use your calculator. I mean, do not be afraid to use that calculator. It's pretty nice because you could use the table feature to just keep getting bigger and bigger and bigger. Or you could use the Y1 feature where you can actually plug values into Y1 and plug in 1,000, plug in 10,000, plug in 100,000, see where it's going. If it's just getting bigger and bigger and bigger, the limit does not exist because you're not converging onto a value. But if you're converging onto a value, chances are there is some type of horizontal asymptote. And with exponential functions, you do have a horizontal asymptote to one side. Logarithmic functions, no horizontal asymptotes. Here's those exponentials again where you do have a horizontal asymptote. And then again, watch out for rational functions. Rational functions are the big one where you definitely have a strong presence of horizontal asymptotes. So those are definitely going to affect your end behaviors, to the left or to the right. So please make sure you remember how to find horizontal asymptotes. That's kind of like really the big sticking point, to be honest, because if you have a horizontal asymptote, then that's definitely going to affect your end behavior, which is essentially the same thing as a limit towards infinity or a limit towards negative infinity. So really this lesson is something that we've already covered because we've already talked about end behavior. We're just instead of using the good old as x goes towards infinity, what's f of x doing? We're using a limit as x goes towards infinity to explain that exact same thing. All right, that's it.